They say the Earth moves in mysterious ways, but the truth can be stranger than fiction. In South Africa, the land is rising, not because of earthquakes or volcanic pressure, not because of shifting tectonic plates or underground explosions. It's rising because of what's missing, not in the sky, not in the rocks, but in the water. This isn't a future scenario or a speculative theory. It's happening right now, millimeter by millimeter, year after year. The ground is slowly, silently lifting upward. And the reason why could reshape how we understand the planet's surface and our impact on it. Between 2012 and 2020, scientists noticed a peculiar pattern emerging across South Africa. The land was rising. In some areas, up to 6 millimeters over 8 years. A tiny amount perhaps, but geologically speaking, that's significant. Initially, researchers suspected this might be linked to mantle plumes, rising columns of hot rock from deep within the Earth's interior. After all, southern Africa rests atop the African superswell, a region of elevated topography long thought to be buoyed by deep mantle upwelling. The superswell itself has long intrigued geologists. Unlike much of Earth's crust, which tends to sink under its own weight over time, this vast area of southern Africa, along with parts of the South Atlantic Ocean floor, sits unusually high. Some theories propose that it's supported from below by a hot, buoyant mantle anomaly, effectively propping the crust up like a raft floating on a rising current of magma. But the recent study published in Journal of Geophysical Research, Solid Earth in April 2025, called this assumption into question, at least in terms of near-term changes. Led by Dr. Makan Kariga at the University of Bonn's Institute of Geodesy and Geoinformation, the research offered a more immediate and anthropogenic explanation: water loss caused by prolonged drought. Using South Africa's robust network of over 30 permanent GNSS stations, high-precision GPS sensors anchored deep into bedrock to detect crustal motion down to fractions of a millimeter, the team analyzed vertical land movement in relation to climate variability. Their results were striking. The most significant uplift occurred in tandem with the devastating 2015 to 2018 drought that brought Cape Town to the brink of day zero. At the height of the crisis, city officials were counting down the days until municipal water would be shut off entirely. Massive conservation campaigns, groundwater extraction, and emergency water shipments kept taps running, barely. But the drought's reach extended well beyond Cape Town. Across much of the country, groundwater reserves were tapped aggressively. Reservoirs dipped to historic lows. Farmlands withered, and the land itself began to move. This wasn't a coincidence. As surface and subsurface water was removed, the mass once pressing down on Earth's crust diminished. Just like a trampoline springs back after someone steps off it, the crust responded to the reduction in weight through a process known as elastic isostatic rebound. Though most commonly associated with glacial melt in places like Greenland and Scandinavia, isostatic rebound also responds to significant hydrological shifts. In this case, climate-driven water loss became the driver. Dr. Kariga and his co-authors used sophisticated modeling to test competing explanations. Could deep mantle processes account for the uplift? Could tectonic forces be subtly at play? Their conclusion was unambiguous. The recent changes in elevation could not be explained by long-term geological processes alone. They matched far too closely with the timing and spatial distribution of water loss. This suggests something powerful. Human-induced climate stress is now significant enough to measurably deform the Earth's crust. It's a sobering thought. The tools we once reserved for earthquake monitoring and volcano forecasting, GPS displacement maps, crustal deformation models, are now needed to monitor what we're doing through drought, agriculture, and groundwater depletion. But the implications go deeper still. Infrastructure may be quietly strained by this uplift. Roads that once lay flat could begin to tilt over decades. Underground pipelines might develop stress points as the ground slowly rises unevenly. Even railways and airport runways may need new tolerances built into their foundations in drought-prone zones. Engineers may soon have to consult not only weather models, but geodesy maps. And the biological systems are shifting too. As water tables drop, the availability of moisture for native vegetation changes. Root systems weaken. Some species vanish. The loss of water not only lightens the crust, but starves ecosystems of their lifeblood. And the land, in turn, reacts with both ecological silence and geological motion. This isn't happening in isolation. Across the globe, scientists are seeing similar signals. In California's Central Valley, the land has sunk in some places due to aquifer collapse, while in nearby regions, uplift occurs where water loss is more diffuse. In India, groundwater extraction has shown to alter surface elevation enough to confuse satellite altimeters measuring sea level. Even in the Amazon basin, seasonal changes in water weight subtly tug at the crust in a yearly pulse. But South Africa's case is unique. Nowhere else has the relationship between human-driven water loss and crustal uplift been so clearly mapped, so tightly correlated, and so crisply modeled. It's a case study that's rapidly becoming a warning. Because if this can happen in South Africa, where topography has long been considered geologically stable, then what about other regions of the world built on even more precarious fault systems? What happens when uplift from water loss meets regions of tectonic tension? Are we nudging the crust towards stress thresholds we barely understand? While no direct link has yet been proven between hydrological uplift and induced seismicity in South Africa, it's a subject now under active investigation in global seismology circles. In Turkey, Mexico, and California, groundwater pumping has already been tentatively linked to minor shifts in fault stress. Dr. Carragher's study hasn't just revealed a local effect, it's opened the door to a global research frontier. And as more data pours in, the message is clear. The Anthropocene is not just a term for the surface of the Earth, it describes a whole Earth phenomenon. Our activity is now so intense, so sustained, and so widespread that the ground itself has started to keep score. And the scoreboard doesn't lie. The numbers are precise, the sensors impartial. Every millimeter tells a story. The ground beneath us is shifting, not in a violent jolt, but in a slow, rising wave of geological memory. And it's rising not because of what we've added, but because of what's been lost. Water, stability, balance. If the Earth is this responsive to a decade of drought, what might it do in the next one? For more stories like this, where climate meets geology, where the planet's silent movements speak volumes, subscribe and stay curious. Because sometimes the biggest transformations are the quietest ones of all.